Let's find the area between curves. That's our topic today. So the problem is to find the area between two curves, and we're going to do this first with a couple of friendly calculus equations. And the two equations are x squared, and then we'll also use the square root of x. So let's go ahead and graph that. Obviously that's my x squared graph, and that's my square root of x. Those are my two functions. Okay. And what we really care about is the area between them. We're looking for the area of the purple region. That's what this video tutorial is on. So let's think about what the formula is. Well, the area of region between f and g, we can call this function f of x if you want, and this one function g of x, or just for simplicity, let's call them functions f and g. If we want the area of that region, then that's going to be equal to the area of the region under f of x, which is this entire thing right here. But then we have to subtract the area under the lower curve. Okay, so that's the area under the lower curve. So you can imagine, you can see that this is way too much. We're overestimating. But once we subtract out this pink part right here, then we're left with just that green part, which is what we want. All right, so that's the formula. And let's go ahead and add some calculus to that. So that's going to be equal to that. And I kind of prefer this formula a little bit better than the other one, but basically what you're doing is you're taking the integral from a to b of your top function minus your bottom function. And then this would be an x value right here, and this would be also an x value right here. And what I mean by that is this x value to this x value. Now, in our particular example, we were talking about the intersection points, but in here we're talking about the area between these two lines, and we'll do both. So in this particular case, go back, we have to identify our top function and our bottom function. Well, our top function was y equals the square root of x. See how that's my top function right there? And my bottom function is actually y equals x squared. So that's the first step, folks, is finding the top and the bottom. So I even like to label that this is my top and then this is my bottom. So again, let me show you that. My top would be what I'm highlighting right here. That's my top, which would be y equals the square root of x. And then my bottom function is y equals x squared. So I've identified my top and my bottom. And you can see here in my answer that I've got my top function minus my bottom function here. And then we're talking about from the starting x to the ending x. And in this case, it's the intersection points. You can see that my x value here is 0, and my x value here is 1. And how can you find that? Well, there's actually two different ways. We'll just be focusing on doing this on our calculator, and you'll see I have a video below this one showing you how to find the intersection points between two curves. But you could have also done the following. You could have set your square root of x equal to x squared. So I'm taking these two equations and setting them equal, because you're trying to find when are they the same, right? So if I square this and square this, I get x equals x to the fourth. I'm going to subtract that to the other side, and I get x to the fourth minus x equals 0. Okay, here I'm going to pull out an x, so I get x cubed minus 1 equals 0. So when do we have x equals 0? Well, when this is 0 and when x equals 1, because 1 cubed minus 1 is 0. So you can see that those actually are our intersection points. That does get more complicated for sure, but you can always use your calculator to find intersection points. Okay, so now that we have this, let's go ahead and actually calculate our definite integral. Remember, this came from my intersection points here and here. This is my top function minus my bottom function. So I'm going to rewrite this integral right now as x to the 1/2 minus x squared dx. All right, so integrating that, I'm going to get x to the, we'll add a 2 over 2. That's going to give me a 3/2, but then a 2/3. And since I'm integrating, I can go ahead and get rid of that integral symbol. And then this is going to be minus x cubed over 3. And we're evaluating it from 0 to 1. So you always plug in your top number first. So this is going to give me 2 times 1 to the 3/2 over 3 minus 1 to the 3rd power over 3, and then this is going to be, you should have big parentheses here. I could be plugging 0 in and doing the same thing as I just did, but I did it with 1. However, I know that when I plug in 0 to all that, I will get 0. And folks, this just becomes a calculator problem, so I'm going to pick up my calculator and do this. And I get 0.333333, or just 1/3. And you could write units squared if you want, because we are talking about area, but I won't be too picky on your units. Now we actually could have done this without a calculator. As you say, 1 to the 3/2 power is just 1, so it's really just a 2/3 minus 1 to the 3rd power is 1. So we really just have 2/3 minus 1/3 is 1/3, which I got the same thing on my calculator. So I just found the area of this right here, the shaded region. All right, how about y equals x minus 2, y equals the square root of x, and y equals 0. Find the area under the curve. Well, to do that, we first have to graph. So my y equals x minus 2, I start here, and then I just draw my line. Remember, my slope is 1, so that's up 1 over 1, up 1 over 1, up 1 over 1. Okay, and then I have my square root of x, which is 0, 0, 1, 1, 4, 2, 2, 3, 4, 1, 2. Okay, like that. And then I also have my y equals 0. So I'm looking for this area right here. All right, now interestingly enough, our top curve and our bottom curve are actually different. So what I'm going to do is draw a bigger picture of this. Hopefully this helps you. So I have something like this, and then something like that. So I'm going to split this up into 2 problems, and you'll see why in a second. We've got the area under here, okay, which I can represent on the graph is right here. But then I also have the area of this right there. Now on my first one, I have a top curve. Just gonna call this my first, my top. This here is my first. It's going to be my top curve is going to be the square root of x, and my bottom is going to be actually the line y equals 0, this one right here. So the bottom is going to be y equals 0. And where does that happen? From where to where? Well, it's a little bit tricky to tell, but it is 2, right? Because you can think about where this graph goes up 1 over 1, up 1 over 1. Well, it hits at 2. So this right here would be from 0 to 2. So it would be from 0 to 2. All right, now let's go ahead and let's talk about our second. I'll use purple again. So we're talking about this right here, this purple section. So my second is going to be from here to my intersection point. And that intersection point is at x equals 4. And if you don't believe me, you could keep going up 1 over 1, up 1 over 1, up 1 over 1. See that we are, in fact, at 4. So our top function here is going to be still the square root of x, but this time our bottom function is this curve right here, which was our line, which was y equals x minus 2. And again, we talked about what our x values were, but they were from 2 to 4 here. So that's going to be from 2 to 4. So to set up this answer, we have to have 2 integrals. We're going to have our top curve minus our bottom, and from 0 to 2. So our top is square root of x minus 0. Okay, I just did this right here, folks. Top curve being square root of x, bottom curve being y equals 0, and that is from 0 to 2. And then I have to add the area of my other integral, and that's going to be from 2 to 4, and this time my top curve is, again, the square root of x, minus, and then don't forget your parentheses, my bottom curve is this whole thing, x minus 2 dx. All right, for sake of time, I'm going to solve this on my calculator, but folks, you know how to find definite integrals, and you can certainly do this on your own. So let me get my answer. I get 3.33333, or 3 1/3, and I don't care how you write that. I'm going to say units squared. And you might say, why is this important? And it actually is hugely important when you think about manufacturers creating things and figuring out how much material they need. Very rarely is something a perfect square, a perfect rectangle, perfect circle. They end up being more of these curved situations. All right, so what I'd like you to do now is kind of watch the video of how I do this problem on the calculator and watch how I find the intersection points on my calculator. So pause this video and do that. All right, you are back. So now we have to figure out what the top curve is, what the bottom curve is, and then add our intersection points. Recall for our intersection points on that video below, we got from -1, that was our x value right here, to 3, that was our intersection point right here. Our top curve is obviously going to be the quadratic that has the negative in it, which would be this one. So we'll have our 18 plus x minus x squared. And then our bottom curve, remember we need parentheses around our bottom curve, is going to be the happy face parabola, which is going to be this one because of the positive x squared. So this is our bottom parabola. Don't forget parentheses. All right, at this point, I'm not going to spend time doing this with a definite integral, doing it out by hand. You are more than capable of doing that, but let me get you the answer in case you want to check your work. I get 21 1/3. We're really into the thirds, aren't we? Units squared. All right, that's it, folks. Make sure you've watched how to find the intersection points on your calculator. And just remember, it's going to be the integral from your x value to your x value of your top curve minus your bottom curve. Don't forget parentheses, dx. Thanks for watching.